So a rational function is any function where you have one polynomial, p of x, in the numerator, divided by the denominator polynomial, and typically when we have a rational function we would encounter problems in the sense there are certain values where the function will not exist. So we have to exclude those values from the domain of the rational function. Finding those values are very easy. All we have to do is set the denominator equal to 0, for instance, and that function set x minus 5 equal to 0 and solve for x, which would imply x is equal to 5. So the domain must not include 5. So in set notation, it's x is all real numbers except 5. And in terms of an interval notation, so we have all values, all real numbers, from negative infinity all the way up to 5, but we cannot include 5, so we put a hole, an open dot, and go all the way up to positive infinity. So we should not be including 5 in the domain. So the interval notation would be negative infinity all the way up to 5, union 5 all the way up to infinity, and as you can see that I'm not including 5. In a similar manner, we want to find the domain of function g of x, so we set the denominator equal to 0, and solve for x, so which would mean x squared minus 25 equal to 0. That would imply x squared equals to 25, which would mean x is plus or minus 5. So in terms of set notation, all x values that are real numbers except x equals 5 and x equals negative 5. In terms of interval notation, this would be negative infinity all the way up to negative 5. We cannot include negative 5. Negative 5 up to 5. We cannot include 5. And 5 up to infinity. The U stands for union. So in part C, we have x plus 5 over x squared plus 25. And if we set the denominator equal to 0, there is no number, no real number that you can plug in for x would make x squared plus 25 equal to 0. So the domain has no problems whatsoever. So in terms of set notation, x would be all real numbers. And in terms of interval notation, it's negative infinity all the way up to positive infinity. So there is this concept of right limit and left limit. So the arrow notation, as you can see here, x approaches 0 and superscript negative. So that would mean x approaches 0 from the left. Likewise, there we would interpret it as x approaches 0 from the right. And there we simply say f of x approaches infinity. And here we would say x approaches negative infinity, in the sense it is decreasing without bound. So over there, x approaches positive infinity, in the sense the value of x increases without bound. So over here, when f of x is approaching infinity, the function value increases without bound. In other words, the y value increases without bound. Likewise, if we say the function values, if f of x is approaching positive infinity, they are referring to this particular graph. So it's increasing on this side, it is going up, and it is increasing on that side. So it is increasing without bound on both sides. However, I would write a side note here, that's where I was going. That would mean the function values are decreasing without bounds. So anytime we have a point where the function is approaching infinity or negative infinity, we end up having a line called a vertical asymptote. The vertical asymptote is an arbitrary vertical line, so which is why we have it as a dotted line. So it is arbitrary. And the function moves along the arbitrary line either toward positive infinity or toward negative infinity. So the behavior of the function is not the same on either side of that arbitrary line, the dotted line. For instance, when we approach -3 from the left, the function is going toward negative infinity. However, when we approach it from the right, the function is going toward positive infinity. So, as we approach negative 3 from the left, we write it as x is approaching negative 3, and the superscript indicates from the left. The function is going toward negative infinity. Likewise, when we approach negative 3 from the right, that plus indicates from the right. The function approaches positive infinity. In a similar manner, we have 1 as we approach 1 from the left-hand side. The function is going down toward negative infinity. As we approach 1 from the right-hand side, the function is going up toward positive infinity. So there is a dotted line on the x-axis, which is y equals 0. And what happens as the value of x keeps on increasing? So as x gets larger and larger, the function is dipping down toward 0. And the same happens on this side. It is getting closer and closer to 0. So as x increases toward positive infinity, the function becomes 0. In other words, as x gets larger and larger, a bigger positive number, the value of the function becomes 0. If x gets smaller and smaller, in other words, it's going toward the left, the function is going toward 0. So how do we find a whole and a vertical asymptote at some x is equal to a? So first step is to get rid of the common factors in a rational function, because we are dividing one numerator polynomial by the denominator polynomial. So the chances are something is going to get cancelled. So, but not always. So we have x plus 2 over x squared minus 4. I could write it as x plus 2 times x minus 2. The x plus 2's would go away. We have 1 over x minus 2. So set denominator equal to 0. And solve for x. This would imply x minus 2 equals 0, so x equals 2. And that is the vertical asymptote, because if you draw a line through x is equal to negative 2, that would be a vertical line, and this is an arbitrary line, so we draw it as a dotted line. The whole is at 2, because the domain would go from negative infinity to 2. We cannot include 2, union 2 to infinity, which would imply the whole is at x is equal to 2. The next problem, as you can see, there are no common factors between the numerator and the denominator. Nothing to cancel here. So we simply set denominator equal to 0. And solve for x, which would imply x times x plus 5 equals 0. So there are two factors that would imply x is 0 or x plus 5 is equal to 0. So that is our first vertical asymptote. The second vertical asymptote is x is equal to negative 5. So the domain starts at negative infinity, goes all the way up to -5. We cannot include -5, so union -5 up to 0. We cannot include 0. Union 0 up to positive infinity. So the holes are at x is equal to 0 and x is equal to -5. So in part C, there are no vertical asymptotes because there is no real number that would make the denominator 0. So if there are no vertical asymptotes, that would simply imply that there are no holes. So now that we looked at vertical asymptotes, we can move on to horizontal asymptotes. So a horizontal asymptote is a horizontal line, an arbitrary line of that sort. So sum y equals b, or y equals -c, and it is a line along which a function goes toward infinity that way, or it could go that way, and so forth. So how do we recognize the presence of a horizontal asymptote? So we're dividing a polynomial by a polynomial. So we have an nth degree polynomial and an mth degree polynomial. So the power is n here. And m there. If the numerator degree is less than the denominator degree, then the horizontal asymptote is always y equals 0. So the numerator degree is less than the denominator degree. But on the other hand, if they are the same, if n is equal to m, all we have to do is divide the leading coefficients of the leading terms. So we'd simply do a divided by b, set it equal to y, and that would be the horizontal asymptote. However, if the numerator degree is greater than the denominator degree, there will be no horizontal asymptote. So in the first example here, the numerator degree is 2, the denominator degree is 2, they are the same, that would indicate no horizontal asymptote. In part B, the numerator degree is 1, the denominator degree is 2. Is 2. So the denominator degree is bigger than the numerator degree. So the asymptote oh, I'm sorry, I kind of messed up here. Going back. So the numerator degree is equal to the denominator degree. So we divide the coefficients, which is 15 over 5. I apologize. So 15 over 5, we get 3. So the horizontal asymptote is y equals 3. So the asymptote, the horizontal one in part B, would simply be y equals 0. And the last case, the numerator degree is 2. The denominator degree is 1. The numerator degree is greater than the denominator degree, so no horizontal asymptote. Perhaps you might have thought when I was doing part A that I was doing something wrong, and if you recognized it, that is actually a good thing. So, asymptotes typically occur with rational functions. That is, say f of x equals p of x divided by q of x. So that is a polynomial. So is the denominator. It's a polynomial such as a quadratic function, cubic function, and so forth. So a vertical asymptote is a vertical line along which the function goes toward positive infinity or negative infinity. This happens when q of x equals 0, i.e. the denominator is equal to 0. A good example, we've seen this before, f of x is equal to 1 over x plus 2. If we graph this, at negative 2, we will have an asymptote. The reason being, when we plug in negative 2, the denominator would become 0. Horizontal asymptote is a horizontal line along which the function approaches 0 or a fixed value. A fixed value of y. And if f of x is equal to p of x divided by q of x, a polynomial divided by another polynomial, the horizontal asymptote is the x-axis, i.e. the line y equals 0 if the degree of the numerator is greater than the degree of the denominator. The horizontal asymptote is the line y equals c, where c is the ratio of the leading coefficients of p of x and q of x occurs when the degree of p of x and q of x are the same. We have seen that the limit at infinity and an infinite limit are not the same. I've mentioned this before. In this problem, what we are looking at is the limit at infinity. So, what happens as x approaches infinity? Prior to applying or finding the limit, let's see if we can factor the numerator. I can factor the numerator as x, let's see. Could we think of two numbers so that when we add, we get -6, and when we multiply, we get 1. Well, that's not going to be feasible. So look at the polynomial x squared minus 6x plus 1 divided by x squared minus 9. So the degree of the numerator and the degree of the denominator are the same. So the limit as x approaches infinity is approximately equal to x squared over x squared. The rest don't matter. So that would give us 1. Another way of looking at it, if you pull x squared out of the numerator, we have 1 minus 6x over x squared plus 1 over x squared divided by x squared 1 minus 9 over x squared. So limit x approaches infinity, x squared times 1 minus 6 over x plus 1 minus x squared divided by x squared times 1 minus 9 over x squared. So those two would go away, and x is approaching infinity. In other words, it is becoming an extremely large number. And I'm dividing 6 by a large number, here in 6 over x, so that is going to become 0. I am dividing 1 by a large number because x is approaching infinity. So in 1 over x squared, as x approaches infinity, that is going to become 0. Same argument applies for negative 9 over x squared. That would become 0. So we end up having 1 minus 0 plus 0 divided by 1 minus 0, which is 1 over 1, we get 1. So we want to evaluate the limit as t approaches infinity, square root of t plus t squared divided by 2t minus t squared. So I have a common factor of t squared. We can't use the trick that we used in the previous problem. Have 1 plus square root of t is simply t raised 1 over 2 divided by t squared. Entire thing divided by t squared times 2t over t squared minus 1. T squared would go away. Limit x approaches infinity, 1 plus t raised 1 over 2. If you bring it to the denominator, you will have t squared times t raised negative 1 over 2. And the second case, we have 2t, 2 over t minus 1. So the limit t approaches infinity, 1 plus 1 over t raised 3 over 2 divided by 2 over t minus 1. So since t is getting larger and larger, 1 divided by a large number is going to go toward 0. And we have 2 divided by a large number as t goes to infinity, so that would become 0. So the limit is simply 1 over negative 1. We end up getting negative 1. You could always verify your answer with the help of a calculator. So what we have here is square root of t, I'll put x, plus t squared or x squared divided by 2t minus t squared. I'm going to put x squared. Make sure you put parentheses properly, and let's graph it. And you can see the curve in the bottom is going toward infinity along the line y equals negative 1. So it's going that way. So y equals negative 1, which is the dotted line here, is the limit, and that would be the horizontal asymptote. In the previous problem, the horizontal asymptote was the x-axis. Oh, no, it was y equals 1. So y equals 1 was the horizontal asymptote. So we want to evaluate the limit t approaches infinity, square root of t squared plus 1. Now, anytime we are looking at t approaches infinity or x approaches infinity, we are looking at the limit at infinity. So pretty much we are looking for the horizontal asymptote. Now, how do we go about this problem? So as t approaches infinity, the value of 2t squared would be greater than 1. So I could approximate it and write it as limit t approaches infinity, square root of 2t squared, which is simply limit t approaches infinity, square root of 2 times square root of t squared. Square root of 2 times t. Square root of t squared is simply t. So the limit here as t approaches infinity is infinity because t here gets larger and larger as t approaches infinity. So limit t approaches infinity, square root of 2t squared plus 1 is infinity. Approximately equal to infinity or just infinity, they are one and the same. So it doesn't matter.